Okay. Yeah. So now we will actually discuss some scheduling algorithms. And specifically, we will discuss these six, which you see here. Okay. Let us start one by one. And let's start with the very first, simplest scheduling algorithm, first come, first serve. As the name implies, this is very simple. It's a non-preemptive scheduling, and the process that requests the CPU first is allocated the CPU first, and the process is allowed to run unless, I mean, until it's voluntarily gives up the CPU. Right? So that is why it is non-preemptive scheduling. And in this very simple process, in this very simple algorithm, the ready list is maintained as a FIFO queue. So just like whatever process comes, it is added to the end of the FIFO queue, and it's very simple first come first serve kind of scheduling, non-preemptive. So let us see this example. Okay. One thing which you will understand is that there is a problem with this very simple scheme, that the average waiting time is long. But let's demonstrate that through this example. So in this example, there are three processes. And let us say, so in a process, we will consider two kinds of entities or two aspects. One is the arrival time. So this is the time at which the process arrives or the process is submitted for the first time. Okay. And this is the CPU burst length. So all these three processes come at the same time, which is the time 0. It's not necessary that all processes come at the same time. We will see other examples later where processes will come at different times. But for now, this very simple example. Let's say all three processes come at the same time, which is time 0. And their CPU bursts are like this. So P1 has a large CPU burst, 24 milliseconds. P2 and P3 have small CPU bursts of 3 milliseconds. Okay. This is the question that I would ask you to do. The first one I'll tell you what to do, and then next one words I'll ask you to do. So draw the Gantt chart and calculate the average waiting time for the two schedules, P1, P2, P3 and P2, P3, P1. So what is a Gantt chart first of all? Let's see. So understand again here we are, as I said earlier, we are focusing on waiting time because that is exactly under the control of the scheduler. And we are looking for average waiting time. That means whatever be the process, all the processes that have been submitted, each one of them have to wait for a certain amount of time possibly. What is the average waiting time for all the processes? So let's consider first the schedule P1, P2, P3. Now the picture you see here, this is a Gantt chart. This basically says the x-axis is time and it tells which process will run at what time. Okay. X-axis is time and this Gantt chart tells you which process will run at what time. So let's consider this schedule P1, P2, P3. Right? So first P1 was scheduled, and as we said, it's a non-preemptive kind of scheduling, very simple. Therefore, it ran for 24 milliseconds. That was the CPU burst time. Then P2 was scheduled. That ran for 3 milliseconds. Then P3 was scheduled. Then it ran for 3 milliseconds. Okay. So what was the waiting time for all these processes? P1 did not have to wait at all. So it arrived at 0 and it started running at 0. So waiting time for P1 is 0. For P2, it arrived at 0, but it started running at 24. So waiting time of P2 is 24. Similarly, waiting time of P3 is 27. So the average waiting time is this, 17 milliseconds. Okay. Any questions here? Okay, if not, let me proceed. Now this is for the schedule P1, P2, P3. For the same example, let us consider another schedule P2, P3, P1. So now you see P2 is scheduled first and it runs for 3 milliseconds. Then P3 is scheduled, it runs for 3 milliseconds. And then P1, it runs for 24 milliseconds. So now the waiting times are for P2 it's 0, right? Because it started at 0 itself. For P3 it's now 3. And for P1 it is 6. So now the average waiting time is 3, which is much smaller than what we had earlier. So see, we consider two schedules in the same example. Well, for P1, P2, P3, the average waiting time was 17 milliseconds. And for P2, P3, P1, it was as low as 3 milliseconds. So the point to note here is, in this first come first serve scheduling, depending on the exact schedule, the average waiting time can be long. Right? So if by chance this schedule is chosen, then the average waiting time would be very high. So that is the one big problem with FCFS. And this effect, which we saw just now, is called the convoy effect, where a process with large CPU burst can delay several processes with shorter CPU bursts. So this is a known problem of FCFS scheduling. It's called the convoy effect. Also, FCFS prefers CPU bound processes. Right. Why is this? Why do you think FCFS, I'm making this statement. Do you agree that FCFS prefers CPU bound processes? Instead of IO bound processes. So why do you think, the answer is given in the slide, but still, why do you think it's this? Okay, I hope I'm audible, right? Okay. Yeah, so the answer that I was looking for was given by Mukul. The main problem is that it is non-preemptive. So suppose several IO bound processes come, even when they are doing IO, so IO bound processes will do lots of IO, right? So as they are doing IO, the processor will not be scheduled to someone else, some other process, because it is non-preemptive, right? So that is the issue. So that is why CPU bound processors are better. So okay, Shubham, that's, what is actually meant by preference here, that is just a way of writing the English. What is meant here is FCFS works, FCFS is not at all a very efficient scheme. Even then, it works slightly better if there are more CPU bound processes. So prefers mean, yeah. So that's the way the English is written. Of course, a scheduling algorithm cannot prefer or cannot have any preference for processes. Whatever processes are there in the system, it has to schedule. Okay, so this is a very simple technique. I hope there are no questions. If not, then I have this question for you. Consider this example, and can you calculate the average waiting time and draw the Gantt chart? So the difference here is that the arrival time is now different for different processes. In the previous example, every process arrived at time 0, but now they are arriving at different times. Okay. So can you take 5 minutes and work this out? Of course, you won't be able to show me the Gantt chart, but yeah, calculate the average waiting time and then write here. Okay. So let's take 5 minutes and work out this example. Remember that the arrival times are different. Okay, several different answers are coming. 4.8, 2 people are agreeing. There are other answers also. So 2 people are agreeing on 6 and 2 people are agreeing on 4.8. Okay. Okay, some agreement for 2.2 seconds also. Wow. Okay, 2.2 seems to be winning. Okay. Okay. Yeah, the answer is 2.2, 11 by 5. Fine. So it's good to see that most of you have got it. This is a very simple example. So I'm not going to work this out here since most of you have got it. I mean the ones who did not get it, just try it out once more. Now that you know the answer. Yeah, the answer is 2.2 or 11 by 5. And it's simple. If even then you cannot do it, then just ask some of your classmates. Many of you have got it. Okay, good. Okay. So that was the first come first serve scheduling, which is clearly not a very efficient way of going ahead. And the one major problem we saw or understood is that if by chance a long process, a process which has a long CPU burst time, by chance if that process is allocated the CPU first, then all other processes have to wait for a long time. That is one specific problem we understood. So that gives intuitively, that gives this idea that okay, then why not schedule shorter jobs first, so that those jobs will be completed and the other jobs would not have to wait for long. Okay. So that is precisely what this next algorithm does, shortest job first. Okay. So shortest job first, we are still considering non-preemptive. Okay. But the idea is that execute the shortest processes first. Of course, now our question is how to know which one is shortest. Okay. There is no easy way of doing this. We will discuss this point, but there is no easy way of knowing this. No process will tell the kernel that, oh, my CPU burst time is this. No process does that. Okay. So what can be done? This is what the standard procedure is followed. Associate with each process an estimate of the length of the next CPU burst for the process. Okay. So this is an estimate. Remember, there is no guarantee that this will be correct, the estimate. But yeah, that's the only thing that can be done. You cannot predict the future, right? So I can understand that if the kernel says that let me understand or let me guess what the next CPU burst time would be for different processes. So essentially the kernel is trying to guess the future or predict the future. There is no feasible way of doing it other than just estimating. Okay. So associate with each process an estimate of the length of the next CPU burst. And when CPU is available, assign the CPU to that process which has the smallest estimate. Okay, second problem for you. Again, for simplicity, let's assume that all these four processes come at the same point of time. Okay. And the CPU bursts are these. These are the estimates. So what is the shortest job first schedule and the corresponding waiting time? So all processes come at the same time, but the CPU bursts are different. This is the estimated CPU bursts. Right. So can you just work this out again? Take a couple of minutes and work this out. Shortest job first. So that process having the shortest CPU burst, in this case P4, should be scheduled first. So maybe just take a couple of minutes and work this out. Okay, most people agreeing on 7 milliseconds. Let me give maybe one more minute. Okay, let's see. Yes, 7 milliseconds is right. So let me actually tell how this is coming. So see, first P. So P4 is the time, process with smallest CPU burst, estimated CPU burst. So first P4 will be scheduled. Okay. And we have said non-preemptive. So P4 will be allowed to run the whole amount of time. So it will run for 3 milliseconds. Then again, see, the rest processes are having CPU burst 6, 8, and 7. So next P1 will be scheduled. So P1 runs from 3 to 9 because it needs a CPU burst of 6 milliseconds. Then comes P3. It runs from 9 to 16 because it needs 7 milliseconds. And finally P2. Okay. So what is the average waiting time? For P4 it is 0. Right? For P4 it is 0. For P1 it is 3. For P3 it is 9. And for P2 it's 16. This is because all the processes arrived at the same time, which is 0. Right? So this is the SJF schedule, shortest job first schedule, and the corresponding waiting times. If you have any questions or doubts, then please write here. Now this I leave to you as a homework. For the same schedule, for the same problem, also work out the FCFS schedule with this sequence P1, P2, P3, P4. And you will see that the FCFS gives a higher waiting time. Okay, this you can do later. I mean, this is one advantage. This example is meant to demonstrate that this is one example of the shortest job first compared to FCFS. It can often result in shorter waiting times than FCFS. Okay, this I leave it as a homework. Now, another homework also here. Okay, Devojyoti has a good question. If the arrival time of the jobs are different, will SJF work the same as FCFS? Okay. If the processes come at different times than FCFS, okay, so both questions are the same from Devojyoti and Ramnivas. So if the arrival times of the jobs are different, then SJF will work in the same as FCFS. Okay, let's think. So since this is non-preemptive, you might think so, but I have some doubts. So what do the others think? If the arrival time of the jobs are different, Is it always the case that SJF will work the same as FCFS? Yeah, so I agree with what Pankaj and Dhrumil are telling. They can be different. Let me give one example. Let's say that, okay, let's just change this example slightly. Let's say, yeah, I mean, this is what Ayush is also saying, etc. Ayush and Devarshi. So let's say P4 is scheduled first, so it runs for 3 milliseconds. Now let's say, okay, so let's say that in case of, let's consider this schedule P1, P2, P3, P4. Okay. So now if they all, I mean, suppose all of them come at, okay. So suppose P1, P2, P3, P4, they come at slightly different times. Okay, that, I mean, we know don't need to go for that much complexity. Let me reword myself. Suppose that a particular process P4 is running now, and while it is running, say some processes like P1, P2, P3 came in this order, right? So P4 is running now. So let's say time equal to 2 milliseconds. Okay, so P4 only came at time 0 and it was scheduled. At 2 milliseconds, P1, P2, P3 came in this order. So FCFS will execute in P1, P2, P3 order. However, SJF will check that, okay, P1 has the shortest burst time, but then P3 has a shorter burst time than P2. So SJF will schedule it in order P1, P3, P2. Whereas FCFS will continue to schedule it as P1, P2, P3. Okay, so SJF may differ from FCFS, irrespective of whether the processes are coming at the same time or different times. Right, so SJF and FCFS need not be the same. Okay. Now next, another homework coming your way. So the shortest job first algorithm gives a guarantee that it minimizes the average waiting time. So it's optimal in a way. So it's optimal. So there is a guarantee that SJF minimizes the average waiting time. The task is to prove it for a set of n processes which say arrive at the same time for simplicity with CPU burst times T1 less than T2 less than T3 less than T4. Right, so without loss of generality, we assume that the n processes have these burst times T1, T2, T3 up to Tn, and they are in this order, like T1 less than equal to T2 less than equal to T3. And let's say there are no further arrivals, like all these processes have come at the same time. Then prove that SJF is optimal, as in SJF will give the minimum average time. I'm not going to prove it here. I'm not also asking you to prove it here. Please keep yourself muted. Venugopal. Venugopal, please keep yourself muted. Okay. Yeah. So coming back, yeah, for these n processes, we are taking some simplifying assumptions, like they come at the same time and no other processes come, etc. But even then, prove that SJF is optimal. I'm not asking you to prove it right now. This is a homework. Any idea how we will proceed? Just like there are different proving techniques, right? You may have come across some. Any idea what would be a useful proving technique for this statement? Exactly. Pankaj, Shaumitro, you have guessed the right thing. You should prove this by contradiction. And so I'm not proving it here. I leave it as a homework for you to figure out. Okay, any questions till now? Otherwise, I have a question. Okay, if not, let me ask the question. Okay, so assume that you will be able to prove this. So then we have just discussed that SJF is optimal. Okay, then why is it not the only algorithm that we are studying? Because this is optimal. Why is it that this is not the only algorithm we are studying? Why are there other scheduling algorithms also? Okay, Drumil has an interesting answer, unfair for large jobs. Yes, true. That is that is a very philosophical question, sure. Unfair for large jobs. Yeah, and again, I mean, I was telling this briefly yesterday that there is a concept of fair scheduling. Okay, I'll talk with Professor Mainak Mandal that whether we can give you some idea of fair scheduling, like Linux nowadays uses a fair scheduling algorithm. That's a bit advanced. So, but I mean, we will see if we can give you an idea of that. But yeah, so that's an interesting thought by Drumil that it is unfair towards large processes. Well, yeah, I mean, but I don't know if there is anything to do, as in, if you try to be fair, very much fair towards large processes, you will also make the others wait for long, etc. So yeah, I mean, sure, that's an interesting answer, but that was not, so that's a good idea, but yeah, that's not what I was looking for. I mean, the more the more blatant problem with SJF is what some others are telling, that after all we are only estimating the burst time, and there is no guarantee that what we estimate is correct. Right, so this proof here, this will, or this theorem here, you might say, this will assume that the estimated burst times are correct, but there is no guarantee that this will happen. Okay, so that is the main problem of SJF. Okay, before coming to that, I see another comment by Shomitra. Let me just spend a minute on that. So Shomitra is saying all processes need to be given CPU allocation within an interval of time. Okay. Why is that? So maybe Shomitra, can you unmute yourself for a minute?
Sir, the timer concept is there for it.
Really?
Means,
So
sir,
what we are discussing, is there timer concept?
No.
Right, no, because we are discussing non-preemptive scheduling.
Yes, sir.
So there is no timer concept here. Okay, fine. So yeah, so but the comment that I wanted to make is that, so what Shomitra has said actually does not apply here. But yes, in modern OS, I mean, there is this timer concept, and that is why such non-preemptive schemes are not used. Also, something that we will not cover in this course, but there are certain special kinds of operating systems where such guarantees are necessary. That means all processes need to be given time, need to be allocated CPU within a particular interval of time. So those processes work with strict deadlines, as in this process should end at by this point of time. So you cannot say, oh, a long process came, therefore that process could not be allocated enough CPU time. That is not possible. There are strict deadlines, as in this process should end at this point of time. Any idea what such operating systems are called? Exactly what Shubham has said. These are called real-time operating systems, right? So we are not going to discuss that thing in this course. This is an entry-level operating system course. But if ever any of you take a real-time course, a course on real-time systems or real-time operating systems, then you will see that those scheduling are much more complicated. I mean, there are specific guarantees need to be given that all processors should get this amount of CPU time at least by this amount of time. I mean, by this deadline. right? So we are not going to discuss those complexities here, but yeah, I mean, such complexities can be there and it might make things scheduling more complicated. So believe me, we are discussing some very simple scheduling algorithms. Actually, scheduling in as a real-time system, etc., can be much more complicated. Okay. So, and we know that, like, what can be an example of real-time OS? Just a diversion maybe, but what can be an example of a real-time OS? Exactly, self-driving cars, or even if you do not go so high up, sure, self-driving cars, flight systems, like there, if you do something, yeah, spaceships, etc. So sure, there if a command is given, a guarantee is needed that it should be executed in the next 1 millisecond. Right? You cannot, I mean, oh, a long process came, therefore it was not scheduled. This is not possible. I mean, a command has been given, it has to be done within 1 millisecond. Otherwise, there will be some big damage to the car or to the flight, etc. And even if you do not, yeah, medical devices too, I'm not sure, but maybe, yeah. And even if you do not go to such high-end systems, think about when you play the video games also. When we play computer games, I mean, we are playing cricket or football or something like that, or we are some like warfare games. Like when you are shooting, you actually want the opponent to feel the bullet in fraction of a second, right? So even for playing this kind of a game, computer game, you might want some real-time guarantees that. But of course, in a computer game, if that guarantee is broken, maybe nothing hugely bad happens. But of course, in a flight or in a self-driving car, or these signals which control railways. So these things are, I mean, they require strict real-time guarantees. Okay, microwave oven, again, I'm not sure, maybe, but again, I mean, maybe not as important as say self-driving cars or flight systems, etc. But okay, let's come back. So this is just to tell you that scheduling can actually be a much more complicated problem than what we are discussing here, right? But we are discussing only simple schedulings. Okay, so now we have understood that SJF cannot be used in practice always, or cannot be, I mean, just by using SJF, you cannot expect optimal behavior because this estimate is what the main problem is. So let us see how people still try to do the estimate. So yeah, the key issue is that how to estimate the next CPU burst time. So typically, the only way to, or the only rational way of trying to predict the future is to learn from history. And that is what the common approach here is. Use exponential average of the measured lengths of previous CPU bursts. So basically, the kernel actually knows how long the previous CPU bursts have been of this process. From that, it will try to estimate the next CPU burst time. Okay. So let Tn be the length of the nth CPU burst. And so Tn, you all know, the kernel knows what the last n CPU bursts of this process have been. And tau n plus 1 is the predicted value of the next CPU burst. This is the unknown. So according to this scheme, tau n plus 1 is estimated as follows: alpha times Tn plus 1 minus alpha times tau n. Okay. What is the significance of, so there are two terms. One is this term, another is second term, this term. What are the significances of these two terms, like physical significances? Note the difference. This is Tn, the first term, and the second term contains tau n. So what is the physical significance of these two terms? Okay, no, see, Tn and tau n, you can say one was actual, another was predicted, but so Tn is the actual. Tn is the actual length of the nth CPU burst. And tau n was the estimate of the nth CPU burst. Okay, tau n was the estimated nth CPU burst, and Tn is the actual nth CPU burst. Right. So what Ayud and Ishan they are telling, or Radhika, they are closer to what I was looking for. So if you estimate, if you expand this, then you will get something like this, right? Because tau n was the estimate of the previous time. Now we are trying to estimate tau n plus 1. Okay, now we are trying to estimate tau n plus 1. Tau n was our previous estimate. So if you expand out tau n, now you will get something like this. So basically what is going on? We have to decide whether we give more weightage to recent history or more weightage to past history, I mean distant history. So one way is to give more weightage to the recent history. Another way is to give more weightage to the past history. So that is what is controlled by this parameter alpha. So alpha varies between 0 and 1. Let us discuss the two extreme cases. Say when alpha equal to 0, that means tau n plus 1 equals to tau n. That means we are not changing our estimate. Tau n was our estimate in the previous time. Tau n plus 1 will be the same as tau n. So the recent history has no effect. Whatever we had estimated previous time, we are continuing with the same estimate. The other extreme is alpha equal to 1. So there tau n plus 1 equals to Tn. So only the most recent CPU burst has effect. So whatever was the previous CPU burst, Tn, that is what we are estimating the next CPU burst will also be. So tau n plus 1 equals to Tn. Okay. We can choose alpha somewhere in between. Like if we choose say alpha equals to 0.5, then we are giving equal weightage to the recent history and the distant history. Okay. So this is typically how this estimate is done. Some weightage is given to the very recent history, like say how much was the exact previous CPU burst, and some weightage is given to the distant past, as in overall throughout the lifetime of this process, what all CPU bursts have this process seen. Okay, I was about to ask for questions. Yeah, I see a question from Shomitra. Will these estimated time for next CPU burst be different for different processes at any given point of time? Of course, that is the whole idea. If say there are two processes in the system, process A always asks for large CPU bursts throughout in their lifetime, whereas process B has been asking for small CPU burst times. So the estimate for A also should be large and estimate for B should be small. And that is exactly how SJF will decide which process to schedule next. So if the estimated time is the same for all processes, then there is no point in doing shortest job for scheduling. Any other questions? Any other question? Okay, Devajyoti has a question. If the processes that are in the ready queue are completely different and there is no correlation, then the estimate will not be good. Devajyoti, I don't understand your question, because what we are discussing, there is no correlation between one process and another. The estimate for a particular process depends on only the previous burst times of that same process. We are not talking about any inter-process correlation or anything like that. So Devajyoti, I did not understand your question. Maybe you can unmute yourself and clarify.
Sir, I wanted to mean that all the processes in the ready queue haven't occurred previously. They are occurring first. Say 100 processes that have first time occurred in the CPU are waiting in the process queue. Then the estimate will not be good.
Sorry. You are saying 100 processes
That
completely
haven't occurred previously.
that have not run previously.
Yeah.
So 100 processes completely, all of them are completely new.
Yeah. You can have different applications independently running.
Sure, of course. See, if at a certain point of time, there are many processes which have not at all run, then I guess there is no way of estimating their next burst times. So I guess some default will be assumed and SJF will proceed. From next time onwards, as these processes start actually running, it will get some estimates of the CPU burst times.
So basically you need some history to schedule the next jobs of such type, right?
If you don't have a history for a particular process, say a process is being scheduled for the first time, then you don't have any history for that, then you will just go ahead with some default value, I guess.
Okay.
So maybe if you remember yesterday we saw a curve that how, I mean, that is a long-term curve over many different systems, that how, what is the usual distribution of CPU burst times, and we talked about exponential distribution, etc. So maybe based on that kind of a distribution from history, I mean from not history of this process but from overall history, maybe from that kind of a distribution you can pick the mean or something like that, and that would be your default estimate for processes which have not run at all. Okay, so Shubham, how to determine alpha? There is no very fixed answer here. Typically people go with 0.5 or something like that. But again, these are like just set from experience. Okay. Of course, I mean, yesterday there was a question that can schedules be learned? Then someone might decide that, okay, alpha is a tunable parameter which they will learn over time, etc. We are not going to discuss those things here. But yeah, I mean, typically alpha would be set by some experienced person. But yeah, if you want to make a really complicated scheduling, then you might learn. But again, remember something. We want scheduling to be very fast. So the more complicated you make scheduling, the more time it would take. But that is something which we don't want. The scheduling, dispatching, we want these to be very fast because ultimately these are all overheads. So just keep that in mind. Maybe you design an excellent scheduler, but which takes 1 millisecond to run. That won't be practical. Okay. Okay, Tanmay says, shouldn't we be considering the previous bursts of the similar type process, not every process? Yeah, okay. I mean, I guess you are also talking about that situation where a process is running for the first time. So how to estimate burst time of that process? Sure, you can. I mean, you are right that maybe not, I mean, a better way would be to not to consider all processes, but only say processes of this particular application and then decide the mean or something like that. So yeah, Somnath, just to clarify, in what we have discussed, the estimate for a particular process is being done based on only the previous burst times of the same process. Right, so whatever was discussed in this slide, the tau n plus 1 for a particular process is being estimated from the previous CPU burst times of that same process. Okay, Shomitra has another question. Will the history remain for a particular session or also after terminating the session? Okay, I get very much afraid when new terms are introduced. Now, what is a session? So unless really necessary, I don't introduce new terms. So what is a session now, Shomitra? when you switch off the computer, okay, I really don't know. When you switch off the computer, whether the kernel stores the history, etc., that I don't know. That depends upon the design of the kernel. Yeah, I really have no idea. Maybe some statistics are stored, but I really don't have any idea. Because, yeah, maybe some global statistics can be stored that, let's say, Microsoft Word, how long are Microsoft Word processes, burst times? Maybe some kind of statistics can be stored. But yeah, I have no idea. I have no actual idea of what kernels do. It might also be that no history is stored. Okay, Tanmay is asking, remembering the burst time of all processes and select them for a particular process. Will not this take time? Okay, so first of all, this slide does not tell of this. So Tanmay, I'm not sure what you are asking about. Please unmute yourself and clarify.
So in the system, all these times of like all the CPU bursts are stored, and
Yeah. Okay, go on.
then if a process A is running, we have to select like for this tau n calculation, we have to select like all the processes in which previous instances of A has run, right, to calculate the tau n. So will not this selecting and like sorting the data will take time, and it can affect the overhead, I think.
Why do you need to sort?
No, sorting, no, not sorting, like hashing and all. So that will take time, right?
Yeah, so let's say in the PCB of a process, let's say, I'm not saying that what I'm telling here is what is done, but just intuitively, let's say in the PCB of a process, there are say 100 slots reserved, so that it will remember the last 100 time slots, or maybe 100 even maybe too much, say last 10 time slots. Okay, let's say. So even then, okay, first of all, okay, no, what I'm telling is not actually right. So to compute tau n plus 1, what do you actually need to do? You need to compute this thing. So basically you need to remember Tn, which was the previous burst, how much it was the previous burst. And you need to remember tau n. So what was the previous estimate and what was the previous actual burst length? Okay. These two things, if you remember, you will be able to estimate tau n plus 1. So basically we are talking about one multiplication, another multiplication and one addition. How much time do you think this will take for a processor? So why are you worried about that time?
So I meant the hashing, like hashing the process, because for process A, we are choosing
What will you hash?
as said before that for process A, we take the instances of A only, which has run before. Like the Somnath asked that. So we have to hash that somewhere, right, in the memory.
Why? This is exactly what I'm telling. Alpha times Tn plus 1 minus alpha tau n. So is just remembering Tn and tau n not enough? Why do you need to hash?
Let's take an example. Like suppose at first the process A has run, then B came, then again A has come. So for tau 3, like for the next A, tau 3, we will take only like the previous A in effect, not B, right? So
Yeah.
so we will have to hash that this is the process A somewhere in the memory. So I am asking that will not this take time?
Exactly. What will you need to hash? Tell me. So let's consider that A and B.
Like,
There are hundreds of processes, but for A, what will you need to hash? For a particular process, what do you need to hash?
it's PCB.
PCB is of course being maintained. That is what we have been discussing over the last week or so. PCB is being maintained. So what extra will you need to do for this scheduling? Say you want to estimate the next the kernel wants to estimate the next CPU burst time. What extra is having to be done?
Okay, sir.
What I think is Tn and tau n has to be remembered, and then using this expression you can figure out tau n plus 1, the next estimate. So remembering Tn and tau n and this value of alpha, I don't think this takes too much time, or doing this operation takes too much time for the kernel. Do you have some other concern?
No, sir, I got it.
Okay. So just to clarify, I don't know if, so this line here, this line in this slide, which I am highlighting, this was meant just for you to understand how the calculation is proceeding. This is not what the system will need to do every time. The system will need to do just this. And for a modern processor, this cannot take a large amount of time. Just 2 multiplications and 1 addition, etc. This cannot take large time. Okay. So yeah, some bookkeeping has to be done, like these 2 values have to be remembered. But well, I mean, that's not too much compared to what many other things have to be remembered. Many other register values, etc. have to be remembered. Okay, Ayushi has a question, will alpha be the same for every process? Again, reasonable question, but I don't know. That will depend upon the OS design, right? So, yeah, I really don't know. Maybe for simplicity, alpha can be kept the same for all processes, but otherwise you may have alpha for different processes, but then what will those alphas be, etc. Those things I really don't know. I really don't think that, okay, I should not say this, I don't know, but I would be surprised if many different values of alpha are used. Okay. Fine. So let's end the class today. We're over time. Let me just one thing. Yeah. Okay. Fine. Yeah. Let's end this class today, and we'll continue tomorrow. Thank you.